The grounding electrode conductor, or GEC, carries high fault currents during electrical faults. These currents can generate strong magnetic fields around the conductor. If the conduit is magnetic, such as steel electrical metallic tubing, or IMT, these magnetic fields can induce eddy currents in the conduit, causing it to heat up and potentially damage the conduit or its contents. PVC conduit is non-magnetic and therefore acceptable for use as a GEC conduit. Aluminum conduit is also non-magnetic, lightweight, and corrosion-resistant, making it a good choice for GEC applications. Standard steel EMT is magnetic and should not be used for GEC conduits due to the risk of eddy currents. The GEC conduit is primarily for protection against physical damage and not for electrical insulation. It is recommended to protect the GEC conduit from physical damage using proper fasteners, supports, and bends. It is generally not necessary to leave the GEC conduit open for inspection or maintenance. However, it may be beneficial in certain cases, such as installations in corrosive environments or where access is limited. Use PVC or aluminum conduit for GEC routing to avoid magnetic interference. Protect the GEC conduit from physical damage using appropriate measures. Openness of the conduit is generally not required but may be beneficial in specific circumstances. The primary reason for using non-magnetic conduit for a grounding electrode conductor, or GEC, is to prevent the induction of eddy currents. Here is a breakdown of the concept. During an electrical fault, a large amount of current flows through the grounding electrode conductor to the grounding electrode and ultimately to the earth. This high current generates a strong magnetic field around the conductor. If the conduit encasing the GEC is made of a magnetic material, such as steel, the alternating magnetic field induces circulating currents within the conduit material. These circulating currents are known as eddy currents. Eddy currents cause heating in the conduit due to the electrical resistance of the conduit material. This heating can lead to several problems. Firstly, the conduit can overheat, potentially damaging the insulation of the GEC or the conduit itself. Secondly, the energy lost to heat reduces the effectiveness of the grounding system. Thirdly, in extreme cases, the overheating could pose a fire hazard. By using a non-magnetic conduit material like PVC or aluminum, the magnetic field does not induce significant eddy currents. PVC is a non-conductive material and does not support eddy current flow. Aluminum is conductive, but its non-magnetic properties prevent significant induction of eddy currents, thus minimizing heat generation. Now, regarding the choice between PVC and aluminum conduit. Both PVC and aluminum are suitable as they are non-magnetic. However, each has its own advantages and disadvantages. PVC conduit is lightweight, cost-effective, and resistant to corrosion. It's easy to install and requires no special tools for cutting and bending. However, PVC is less mechanically robust than aluminum and can be susceptible to damage from physical impact or extreme temperatures. Aluminum conduit is stronger and more resistant to physical damage. It also provides better electromagnetic shielding compared to PVC. Aluminum is more expensive than PVC and requires specialized cutting and bending tools. Also, aluminum is conductive and can corrode in certain environments, particularly when in direct contact with dissimilar metals. Standard steel EMT, or electrical metallic tubing, is a type of steel conduit commonly used for electrical wiring. Steel is a magnetic material. The use of steel EMT for a GEC is problematic due to the reasons I discussed earlier regarding eddy currents. The magnetic properties of steel cause significant eddy current induction when the GEC carries high fault currents. This can lead to overheating and potential damage. The purpose of encasing a grounding electrode conductor in conduit is primarily for physical protection. The GEC is often run in areas where it could be exposed to physical damage from impact, abrasion, or other mechanical stresses. Conduit provides a protective barrier to prevent damage to the conductor, ensuring the integrity of the grounding system. While the conduit provides physical protection, it is not intended to serve as electrical insulation. The GEC itself is an insulated conductor, and the conduit provides an additional layer of protection against physical damage, not electrical faults. Whether to leave the GEC conduit open or closed depends on the specific installation conditions and requirements. Here are some considerations. In most standard installations, there is no specific requirement to leave the conduit open for inspection or maintenance. The primary concern is to ensure that the conduit is properly installed and provides adequate physical protection to the GEC. In corrosive environments, such as areas with high humidity, chemical exposure, or salt water, it can be beneficial to leave the conduit open. This allows for periodic inspection of the GEC and the inside of the conduit for signs of corrosion. Early detection of corrosion can prevent potential failures of the grounding system. In areas with limited access, such as underground installations or confined spaces, leaving the conduit open can facilitate easier inspection and maintenance. It allows technicians to visually check the condition of the GEC without having to remove the entire conduit. Leaving the conduit open may increase the risk of physical damage to the GEC, particularly in areas where it could be exposed to impact or abrasion. In such cases, it may be preferable to keep the conduit closed to provide maximum protection. To summarize, the choice of conduit material for a grounding electrode conductor is crucial for ensuring the safety and effectiveness of the grounding system. Non-magnetic materials like PVC and aluminum are preferred to avoid the induction of eddy currents and associated heating problems. The conduit serves primarily to provide physical protection to the GEC, and whether to leave it open or closed depends on the specific installation environment and maintenance requirements. Grounding electrode conductors, or GECs, play a vital role in electrical safety. They provide a low impedance path for fault currents to return to the source, which helps to quickly trip over current protection devices like circuit breakers or fuses. This minimizes the duration of electrical faults and reduces the risk of electric shock, fire, and equipment damage. The NEC, or National Electrical Code, provides specific requirements for GEC to ensure they perform their intended functions safely and effectively. Firstly, the NEC specifies the minimum size of the GEC based on the size of the service entrance conductors. The larger the service entrance conductors, the larger the GEC must be to handle potential fault currents. Secondly, the NEC specifies the materials that are suitable for GEC. Generally, GEC must be made of copper, aluminum, or copper-clad aluminum. The choice of material depends on factors like cost, corrosion resistance, and conductivity. Thirdly, the NEC requires GEC to be installed in a manner that protects them from physical damage. This typically involves running the GEC in conduit or other protective raceways. As we've discussed, non-magnetic conduit is preferred to avoid eddy current issues. Fourthly, the NEC specifies the methods for connecting the GEC to the grounding electrode. Connections must be made using listed connectors and must be accessible for inspection and maintenance. Fifthly, the NEC requires the GEC to be continuous and unbroken. Splices are generally not allowed in GEC as they can increase impedance and reduce the effectiveness of the grounding system. There are different types of grounding electrodes that can be used, depending on the site conditions and the type of electrical system. Firstly, ground rods are commonly used, especially for residential and small commercial buildings. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to a specified depth. Secondly, ground plates are flat metal plates that are buried in the earth. They provide a larger surface area for contact with the earth compared to ground rods and are often used in areas with poor soil conductivity. Thirdly, underground metallic water pipes can be used as grounding electrodes if they meet certain requirements. The water pipe must be in direct contact with the earth for a minimum length, and the connection to the pipe must be made within a certain distance from the point where the pipe enters the building. Fourthly, concrete encased electrodes, also known as UFERs, consist of a length of rebar or bare copper conductor encased in concrete. UFERs are typically installed in the footings or foundation of a building and provide a very effective grounding electrode due to the large contact area with the earth. Proper installation of grounding electrode conductors and grounding electrodes is crucial for ensuring electrical safety. Improperly installed grounding systems can be ineffective and may even create hazards. Firstly, ensure that the GEC is properly sized according to the NEC requirements. Using an undersized GEC can result in inadequate fault current capacity and increased impedance. Secondly, use listed connectors for all connections to the grounding electrode and to the service equipment. Improper connections can lead to increased impedance and reduced effectiveness of the grounding system. Thirdly, protect the GEC from physical damage by running it in conduit or other protective raceways. Damaged GEC can become ineffective or create hazards. Fourthly, ensure that the grounding electrode is properly installed according to the manufacturer's instructions and the NEC requirements. Improperly installed grounding electrodes may not provide adequate contact with the earth. Fifthly, periodically inspect the grounding system to ensure that all connections are tight and free from corrosion. Corroded or loose connections can increase impedance and reduce the effectiveness of the grounding system. The grounding system should be tested periodically to verify its effectiveness. Ground testing involves measuring the resistance between the grounding electrode and the earth. A low resistance value indicates a good connection to the earth, while a high resistance value indicates a problem with the grounding system. There are several methods for testing ground resistance. Firstly, the 3-point fall-off potential method is the most common method for testing ground resistance. This method involves driving two auxiliary ground rods into the earth and measuring the voltage drop and current flow between the grounding electrode and the auxiliary ground rods. Secondly, the clamp-on ground resistance meter is a convenient tool for measuring ground resistance without disconnecting the GEC. This type of meter clamps around the GEC and injects a test signal into the earth, measuring the resulting current flow. Thirdly, the 2-point method is a simplified method for testing ground resistance that can be used when it is not possible to drive auxiliary ground rods. This method involves measuring the resistance between the grounding electrode and a known good ground, such as a metallic water pipe. The electrical codes and standards play a critical role in ensuring electrical safety and preventing electrical hazards. These codes and standards are developed by organizations like the NEC, the IEE, and the UL, and they provide detailed requirements for the design, installation, and maintenance of electrical systems. Firstly, compliance with electrical codes and standards is mandatory in most jurisdictions. Electrical inspectors enforce these codes and standards to ensure that electrical installations are safe and compliant. Secondly, electrical codes and standards are constantly evolving to keep pace with new technologies and changing safety requirements. It is important for electricians and electrical engineers to stay up to date on the latest codes and standards. Thirdly, electrical codes and standards cover a wide range of topics, including wiring methods, overcurrent protection, grounding, bonding, and equipment installation. Fourthly, electrical codes and standards are based on sound engineering principles and best practices. They are developed through a consensus process involving experts from industry, government, and academia. Fifthly, compliance with electrical codes and standards can help to reduce the risk of electrical shock, fire, and equipment damage. The safety of electrical systems relies on proper grounding and bonding techniques. Grounding provides a low impedance path for fault currents to return to the source, while bonding ensures that all metallic parts of an electrical system are electrically connected together. Firstly, grounding helps to protect people from electric shock by providing a path for fault currents to flow back to the source, tripping over current protection devices. Secondly, bonding helps to prevent voltage differences between different metallic parts of an electrical system, which can create shock hazards. Thirdly, grounding and bonding are essential for protecting sensitive electronic equipment from damage due to voltage surges and electromagnetic interference. Fourthly, proper grounding and bonding techniques are specified in electrical codes and standards. Fifthly, grounding and bonding should be inspected and tested periodically to ensure their effectiveness. In conclusion, grounding electrode conductors, or GECs, and their associated conduits are essential components of electrical grounding systems. The use of non-magnetic conduit materials like PVC or aluminum is crucial for preventing eddy current losses and ensuring the safety and effectiveness of the grounding system. Proper installation, inspection, and testing of grounding systems are essential for protecting people and equipment from electrical hazards. Understanding the reasons behind these requirements, such as the properties of magnetic fields and eddy currents, helps in maintaining safe and compliant electrical installations. The principles discussed here form the foundation for sound electrical practices and contribute to a safer electrical environment. These considerations collectively contribute to the overall integrity and safety of electrical installations.